Good day. I am Kaiser Ulama, together with Amanur Abu and Kianju A. Makapagal. We will tackle about the Module 5 performance task. The plots of dimensionless pressure change are known as Ramey's types curve. Time change TD versus dimensionless time change, the skin factor, the dimensional Welber storage constant CSD may be used to identify these curves. For an infinite acting reservoir, specifying CSD, NS uniquely defines the value of PD at a given number or given value of TD. The curves were created using boundary conditions and analytical solutions to the diffusivity equation. The Welber damage or stimulation is defined by the skin factor. As we have seen, this causes an additional pressure drop APS across the altered zone in terms of the skin factor. Figure 8.1 is a log-log plot of PO versus TD with parameters S and CST. Successful application of Ramey's type curves depends significantly on our ability to establish the correct value of CSD to be used for curve matching. Throughout the presentation for pressure drawdown or build-up analysis, we will tackle the steps necessary for a Ramey's type curve. Also, Table 8 to 1 through 8 to 5 from the Oil Well Testing Handbook by Chaudhry are to be used in this discussion. Step 1. Plot delta P versus time on log-log paper the same size as Ramey's type curve. Step 2. If the test has a uniform slope region, 45 degrees line at earliest times, choose any point T on the unit slope line and calculate the Welber storage constant CS. Step 3. Calculate the dimensionless Welber storage constant. Step 4. If a unit slope line is not present, CS and CSD must be calculated from the Welber properties. Step 5. Using type curves with CSD as calculated in steps 2 and 3, find the curve that best fits all the plotted data. Step 6. Note that the values of the match point, the quantity of PDM, the quantity of delta PM, and the quantity of T or delta T, M, and values of S. Step 7. Calculate the permeability K from pressure match point. Step 8. Calculate the porosity CT from the time match point. And the last step, compare the value of porosity C sub T with values used to determine C sub SD from C sub S. So we will get the porosity of C sub T is equal to 0.894 CS over HR2 WCSD. One of the main features of these type curves is that they permit detection of the correct straight line in a conventional semilog plot.
So now, the example 8.1, analyzing drawdown tests using Ramey's type curves. We have the given data for the drawdown test. The reservoir datum is 4,500 feet, temperature 200 degree Fahrenheit, QO 500 STB per day, PI 3000 PSI, PSC 14.65 PSIA, API 18 degree, height 56 feet, O 0.2, UO 0.8 CP, BO 1.2 RB per STB, RW 0.3 feet, tubing size 2.25 inch, and CT 1 times 10 raised to negative 5 PSI negative 1. So for the solution, using Ramey's type curves, figure 8.2 is a plot of table 8.6 on log-log graph paper of the same scale of the type curves of figure 8.1. From the unit slope line on which the data lie for T less than or equal to 0.1 R using equation 8.6. So next slide is we got the pressure difference. And figure 8.2, we're in the pressure drawdown test analysis using Ramey type curves. And in table 8.6 pressure drawdown test data, We got the value from the time 0.0109 to 16.4000 and their respective value. So now, the CS, this computation gave us of a 0.0116 RB per PSI. Then from equation 8.5, the CSD is equal to 1.03 times 10 raised to 3, approximately 10 raised to 3. Using equation 8.9, the value of our K would be 10.3 MD. From the time match point, find the product OCT by using equation 8.10. The value of our OCT would be 1.957 times 10 raised to negative 6 PSI negative 1. Comparing those with the values used to determine CSD from CSD ICS, we obtain OCT is equal to 2 times 10 raised to negative 6. From Rame's type curves, S is equal to 5.0. And from previous computation, the value of CSD is approximately 10 raised to 3 and the value of K is 10.3 MD. So from the time match point, find the product OCT by using equation 810, wherein we got the value of 1.957 times 10 raised to negative 6 PSI. So, conventional method. So, figure 8.3, pressure drawdown data semi-log plot. So, in the y-axis, we can see the flowing bottom hole pressure, PWF in PSI. So, flowing time, T in Rs. So, slope, M is equals to negative 140 PSI per cycle. So pressure per 1 R or pressure 1 R is equals to 1765 PSI. Semi-log plot. So K is equals to 9.96 millidarcy. Askin factor is equals to 4.84. Time and start of the pseudo steady state period TPSS is 15 hours. So, permeability K is equals to negative 162.6 times flow rate times viscosity times formation volume factor all over HM. So, it is equals to negative 162.6 times 500 times 0.8 times 1.2 all over 56 times negative 140. So, we get 9.96 millidarcy. And for S, skin factor is 1.151 times the quantity of Pi minus P per 1 R all over M minus log times the quantity of K times porosity times viscosity times compressibility times well-bore radius squared. So, when we substitute the value, so 1.151 times the quantity of 3000 minus 1765 all over 140 minus log times the quantity of 9.96 all over 0.2 times 0.8 times 10 raised to negative 6 times 0.3 squared. So we get 4.84 for RS. So example 8.2, analyzing build-up test using Raman type curves. So figure 8.4 shows a linear plot of pressure drawdown test data. So pressure build-up data tests are given in table 8.7. Additional pertinent data are given. So reservoir datum is 4,500 feet. Reservoir temperature is 200 degrees Fahrenheit. Porosity 0.039. Oil viscosity 0.8 Cp. So oil formation volume factor 1.136 RB per STB. So well-bore area is 0.0218 feet squared. So pressure 51.50 lb per cubic feet. The last production rate is equals to 250 STB per day. API degrees
40 degrees. Cumulative production at shut in time is equals to 141.979 mstb, and pressure prior to shut in PWFO is equals to 3,534 psia. So solution, figure 8.5 is a plot of table 8.7 on log per log graph paper of the same scale of the type curves of figure 8.1 from the unit slope line on which the data lie for t is equal or greater than t is equals to or lesser than 0.8 hours using equation 8.6. So table 8.7, so pressure buildup test data. So we can check here the pressure buildup test data. So as we can see, the time range and also the pressure it's equivalent to. And for figure 8.5, the log to log data plot. So see, SD is equals to 0. So S in factors is 5. So unit slope line change in time is equals to 0.1. So change in pressure is 100. So the end of well-bore storage effect and the beginning of boundary effect, as you can see. So for its y-axis is the change in pressure, and for the x-axis is the shut-in time in hours. So CS is equals to oil flow rate times oil formation volume factor over 24 times the quantity of T all over pressure Ws minus pressure Wf, point on unit slope. So CS is equals to 250 times 1.136 over 24 times the quantity of 0.1 all over 100. So it equals to 0.01183 bbl per psi. So then, using equation 8.5, the dimensionless well-bore storage is CSD is equals to 0.894 times CS all over porosity times compressibility times thickness times well-bore radius squared. So equals to 0.894 times 0.01183 all over 0.039 times 1.7 times 10 raised to negative 5 times 69 times 0.198 squared. So it equals to 5.90 times 10 raised to negative 3. Using the well-bore properties, the well-bore storage constant from equation 8.7 is CS is equals to 25.65 times well-bore area all over pressure is equals to 25.65 times 0.0218 all over 51.50. It equals to 0.01086 bbl per psi. And CSD, or dimensionless well-bore storage, is equals to 0.894 times CS times all over porosity times compressibility times thickness times well-bore radius squared. So equals to 0.894 times 0.01086 all over 0.039 times 1.7 times 10 raised to negative 5 times 69 times 0.198 squared is equals to 5.42 times 10 raised to 3. So K permeability is equals to 141.2 times flow rate times oil formation volume factor times oil viscosity all over H, or thickness, times the quantity of PD M all over the change in pressure M. So equals to 141.2 times 250 times 0.8 times 1.136 all over 69 times 14 over 850. So we get 7.67 millidarcies. So from Ramis type curve, S is equals to 5.0. That's all. Thank you.